Section 7.2, Part 1, Volumes. This will be volumes by cross-section. Now recall that the underlying principle for finding the area of a plane region is to divide the region into very thin strips, we called that the representative rectangle, and approximate the area of each strip by finding the area of the rectangle, then use the approximations to find a Riemann sum to produce the approximate area for the region. Now by letting the width of each strip approach 0, in other words, delta x goes to 0, this method actually produces the integral. Area is the integral from a to b of f of x dx, provided f of x is positive over that interval, the closed interval a to b. Now, a similar strategy can be used to find the volume of a solid. And what makes this work is the fact that a thin slab has cross sections that do not vary much in size or shape. So it's easy to approximate the volume. Now let us consider a loaf of bread that's sliced, and we're going to go old style with that loaf, you know, the nice square slices. And you can remember you pick it up in the bag at the grocery store and it's got a whole lot of slices. And let's say that the length of the side is 4 and the height, we'll call this delta x. And so we know that the area of the base of this slice is 16 square inches. And we know that we're going to call that slice about ½ an inch thick. Okay, we don't need calculus to find the volume of this because we just have each little slice. And so we can take all of the slices, let's say there's 24 in the loaf, and we can find the volume by taking the height times the area of the base. Okay, no calculus needed. So also let's think about, you know, a sausage. If you buy a sausage at the store and they have it sliced, or maybe you buy one of those round loaves of cheese and you have it sliced. So our cross section here would be a circle. And let's let the radius be 20 millimeters. So we know the area of our circular base is 400 pi square millimeters. And let's call that delta x, that height, to be 0.5. And let's let there be 30 slices in our sausage or loaf or in our cheese loaf, whatever it is we got. And so our height would be 15. And our volume would be 60,000 pi cubic centimeters by doing the volume as the area of the base times the height. Again, this is geometry. You don't need calculus. Why? Because each of those slices is the same size. Okay? So this leads us to, when do we need the calculus? It was easy to find the volumes of these items because the size of each cross section didn't vary. So no calculus was needed. The volume is the sum of the individual slices. The volume was found by taking the area of the cross section and multiplying it by the height of the solid, or the thickness of one slice, times the number of slices, which is consistent with finding the volume of a solid using geometrical properties. Now, when you studied solids in geometry, they were right solids, meaning that the axis running through them intersected the base at its center and was perpendicular to the plane of the base. Let's remember that was a geometry rule you need. But this fact leads to the general volume formula for a solid sliced into cross sections. The volume is the integral from a to b of a of x. A is a area that is a function of x if we're slicing on the x-axis. This formula will be used with the sizes of the cross sections vary. Now delta x is the same as dx, which is the height of each cross section. If we're slicing on y-axis, then it would be area as a function of y and dy. So, all right, let's look at an example. Finding the volume of a right circular cylinder cone with base radius 1 and height of 4. So the radius here is 1 and the height of our cone is 4. Notice that as the slices get closer to the base, they get larger. So this is how we know we need calculus, because the slices are changing. Find the area of one slice in terms of x and integrate over the interval with respect to x. Well, I'm going to go from 0 to 4. And so what I know is I have some similar triangles here. Oh yes, they're back. And my r of this slice, wherever the slice is that I put it, okay, the radius to the radius of 1 equals where I am on x to the whole thing, which is 4. So small radius to big radius, small height to big height. And so now we get our radius as a function of x. Let's look at that volume formula. The integral from a to b, the area of the cross section. My cross section is a circle. The area of the cross section's dx. Volume, area of x, dx. From 0 to 4. My area as a function of x. My radius is x over 4. This is a circle. It is pi r squared dx. And now that's setting it up. Now let's do the calculus of anti-differentiating. And now this is a definite integral. So we're going to substitute 4 in, subtract, substitute 0. Well, that's nice when you get to subtract 0. And we get 64 times pi over 48. What goes into 64 and 48? Let's see. 4 does, 8 does, 16 does. 16 goes into this 3 times and into that 4 times. So there's our volume. Now, did we actually need calculus for this one? No, because we can find the volume of this whole thing because it's a cone. And we know that the volume of a cone is 1/3 area of the base of the cone times the height. But I wanted to use an example that let you see that by using the calculus and dividing this into several slices and taking the volume of one little slice, one representative slice, and then making an infinite number of slices from 0 to 4, I get my actual volume. So I can have different slices and different bases. If we look at this, our base is clearly a circle. You can see the different colors here. Each of those is letting you see we have a slice. And if I look at the side of this, I can see that each cross section appears to be a square. And if you look, this is what this solid is going to look like. Now, why do I need calculus for this? Because look at that curvature. That's not something you can do by just regular volume formula. Look at that curvature that's across the top. Okay? This needs calculus to find that volume. Okay? So the length of each slice is on this base. Okay? And so each of these slices has different lengths. But I do know the area function for a square. So I would find the area of the square times, guess what? If these are slicing along the x-axis, that's a dx. Here's one like the first one with a circle base, and the cross sections were squares. Again, it's really pronounced. If you look at this, look at the side of that. See the top, how curved that is? We have the same thing going on with the side as well. So here's another solid. Again, the base is a circle. My cross sections are equilateral triangles. So you know a formula for equilateral triangle area is side squared times the square root of 3 over 4, or the square root of 3 over 4 times side squared might be a better way to write it. And you can see what the shape of this looks like. Okay? So here is that circle bottom, the equilateral triangle as my cross section, and here's a cross section. And you can see, well, if you could see it in person, you would see that this side is slightly slanted. Okay, that's because it's going towards the bigger part of the radius of the base. Now we have to look at what do we do? How do we find the volumes of these solids using calculus? So the work involved is find the volume of a solid whose cross sections are squares. So we're going to be finding areas of squares perpendicular to the x-axis. That's important. That tells us if we are looking at dx or dy. And that means my area of the squares has to be in terms of x. And this is the tricky part, whose base is formed by the region bounded by the graphs of x equals y squared and x equals 6. Now we know x equals 6 is a vertical line crossing the x-axis at 6. This is a horizontal parabola. So what I'm going to do is show you what this would look like. Here is my y-axis. Here's my x-axis. Here's the line x equals 6. Here's my square cross section. I just have one slice. In order to find the area of the square, we need to know how long this side is. Well, how do we find how long that side is? Let's take this base region and write it two-dimensionally. Okay, so this is the parabola y squared equals x. So for each x, two different y's. And if I took y squared equals x and solved it for y, I would take the square root of both sides, and that is a plus minus because I have the positive part of the parabola here and the negative part of the parabola here. But I need to find the length of this representative slice. Well, what do I know? From the x-axis up to here is a length of square root of x. This is taking me to y equals the positive square root of x. The length from the x-axis down here, we are going to the graph of the negative square root of x, but the distance is still square root of x. So how long is one side? Square root of x plus square root of x. 2 square roots of x. And you'll notice I've drawn a picture of my slice. So here's my slice that's represented here. The length of the side is 2 square root of x. I know that my slice is intersecting the x-axis, which means my integral is going to have dx. So my area of my square needs to be in terms of x, and the area of a square is side squared, which becomes this. So my area as a function of x is 4x. Now, what are my limits of integration? We're going from 0, where the x is 0, out to where x is 6. So here is our setup for our integral. I need to see your setup. Let's kind of get it a little fixed so that it is easy to integrate. Factor out a 2, and that lets this be the integral from 0 to 6 of 2x, which is x squared, from 0 to 6. So it's 2 times 6 squared minus 0 squared, or 72 cubic units. See? Nice and easy. Not anything to be scared of. We can look at other. Here is a base. Same idea. But look at my cross sections. They're semicircles. Here we have kind of the same base. You have to kind of imagine it. And here's my cross sections, which are squares. Another one with the same kind of equation. Got my x equals y squared. But this time, those cross sections are quarter circles. So we can have a lot of fun with this information. Here's another. We'll look at these. These are very, very old. My students created these back in 2000. Your TPs for this section come from the lecture manual, numbers 1 and 2. See you next time.